Hello, my dear NEET warriors. Welcome to the day one of your Navratri challenge. And yes, you are watching your favorite Captain Shreyas Sir on the Vedantu NEET English channel. All the warrior Pandus and Champas, gather along, get your friends, because it's time to start with the day one of the challenge. And these 9 days, you have made a promise that you are going to attend each and every class, sit as long as it takes, and complete these chapters so that 90 marks are pakka in your NEET score of 2025. Just imagine 90 marks just for you. High weighted chapters, high priority chapters, at least you will see two questions, three questions from each lecture, which means even if you are doing close to around 20 to 25 questions pakka in your syllabus, in your question paper. So 25 into 4 is 100 marks. Remember that. So that is what we are targeting in these 9 days. So get ready for the chapter of momentum and collisions with none other than your capto, your Captain Shreyas Sir. And mark your attendance if you have not done that yet. And also subscribe to the Vedantu NEET English channel, because then you will lose track and you will not be in the day 2 of the challenge. So quickly subscribe so that you don't want to miss any of the content in English. And a very, very happy Navratri. Why not get you guys on the screen itself, because such lovely wishes, and you can see our teachers so well dressed, guys. Gopika ma'am is missing, but Gopika ma'am will come here soon. Don't worry. You have your Diksha ma'am, you have your Baswa sir. Yes, this is day 2, this is day 3. All of us for you guys. Make sure you're going to each and every class and marking your attendance by hitting that like button. All right. So let's begin with the lecture, and let's also have a look at everyone. Hi Krishna, Disha, Madhumati. Welcome guys. Yes, nice to see all of you. Hello Harbor, and you are here too. Nice guys. All the warrior Pandus are over here. Great. So, ready for the challenge? Ready for the chapter of momentum and collisions? Expect at least one question. There is a good chance there will be 2 to even sometimes 3 questions. Sometimes the questions are mixed. Sometimes they might combine the concept of momentum, kinetic energy, or collision, or these conservation of momentum principles in some other chapter, maybe electrostatics, maybe gravitation, maybe Newton's law, somewhere or the other. Okay, so let's start. Hi Pratibha, hi everyone, hi Madhuri, hello Mr. Vati, hi Tanuja, nice to see all of you. Yes, ready Captoji, awesome, great. Let's begin. Let me also tell you that today we have some amazing animations as well as some simulations to make you feel how collisions exactly look like. It's going to be real fun, guys. We're going to have fun with not just one-dimensional collision, but also two-dimensional collision, guys. This is going to be real fun. Okay, so let's begin with this chapter. All right, liked everyone? Subscribe? Done? Okay, so let's begin. Oh, I need to remove this or else I won't be able to see. This was just looking cool, right? So I thought I will wear this. Whenever I have to look cool, just remind me, I'll wear this. Okay, happy Navratri. Thank you so much, guys. Happy Navratri. Means a lot. We are not dancing today. Yeah, we'll dance next year in AIMS. Not now. Next year. I don't know the steps, but I'm pretty sure you guys can teach me. Okay, right? All right. So, momentum. We'll start off with this main term, which is called momentum. You know why we are doing this Navratri series? For momentum. We'll be like, sir, momentum, mass into velocity. So, sir, if I have mass and if I start moving, will I get momentum? Physics wise, yes. But studies wise, I want you to gather that momentum. They say that once you start studying, then continuing studying is easier. It's like Newton's law, right? But to get to that studies, to get that mood is the most difficult part. And that's what the challenge is. Trust me, these 9 days, if you sit right, you will automatically get that mood. So when a mass, or in fact a large mass, has a large speed, it has a large momentum. If it's a teeny mini mass, like a small stone moving with andu pandu speed, that's it. It has very low momentum. So momentum is the effect of mass and velocity is the effect of mass and velocity. So if I have some mass over here, if this object is moving with certain velocity v, then the momentum is exactly in that direction. Let's say call the momentum as p. P is the symbol for momentum. It's a vector quantity. This momentum is mass times your velocity. Remember, momentum is a vector in the direction of the velocity. In the direction of velocity. Wherever the velocity is, that's where the momentum is. So how about just highlighting this formula? Of course, oops, what just happened? Okay. If you ask me what is the unit of momentum, so momentum is vector, we did this. The SI unit, or just basically the unit of momentum is kg meter per second. In CGS, it is gram centimeter per second. That is the formula for momentum and the unit of momentum. Great. You can also write momentum in slightly different forms like follows. See, kinetic energy was momentum square by 2m. We have seen this in work energy chapter. We have seen this in work power energy chapter, right? So if you don't remember it, no issues. Momentum is mv. I can just multiply by another mv over here, and I can also divide by mv and all of that. You will see I can somehow write kinetic energy, which is half mv square, as half mv into mv divided by m. This thing over here is nothing but momentum into momentum, so it becomes p square by 2m. Half mv square, I can just write mv here separately. This extra mass which came, I just divided by m, so it will become p square by 2m. Therefore shifting that 2m onto the other side, it will become 2mk. Hence, I can also write momentum is nothing but 2 times of mass times our kinetic energy, but whole thing under the root. So this is also an alternative way of calculating the momentum of the body. It's an alternative way of calculating the momentum of that particular body. Is that right? Everybody till this point absolutely clear? Great. Okay. So now that we understand momentum, if let's say for example, I tell you, a pandu of 3 kg mass has 600 joules of energy. Find his momentum and speed. Find his momentum as well as speed. So like we can see over here in this particular question, mass of the person is given, kinetic energy is given. To find the momentum, we can use this formula. Momentum is root 2 mk. Momentum is basically root of 2 times mass times kinetic energy. The mass of the pandu is basically 3 kg. The kinetic energy of pandu is basically 600 joules. So guys, 2 3s are 6. Again one 6 is there. Again this 100 is there. So 6 is square is 36. Root of that is again 6. 10 square is 100. That means 100's root will be 10. So the answer will be 60 kg meter per second. That is your momentum. But that's not the story's end. We have to also find velocity. Momentum is mass times velocity. Momentum is 60. Mass is 3. So how much would the velocity be? 60 by 3, which is 20. So 20 meters per second. So 20 meters per second. Very good, Pratibha Nag. Yes, Krishna, that is the correct answer for the momentum. And yes, Madhumati, that is the correct answer for the momentum as well. Yes, and the speed will be 20 meters per second. Very straightforward application of this formula. I hope everybody understood how this formula is useful for calculating kinetic energy or momentum or speed or mass or momentum. Whatever is given, the other thing can be found out very easily. But there are many cases where basically the momentum will definitely change. There are many cases where momentum will change. Can you think of examples where momentum changes? So, examples where the momentum changes. Examples where momentum is changing. There are so many examples. Think about it. Imagine there is a ball. Imagine there is a ball. Somebody takes a bat and hit it. Hit with a bat. Hit with a bat. What are you hitting? Hit a ball. Hit this particular ball with a bat. Obviously, it was initially maybe at rest. So immediately after some time, because of the hit, it gains some velocity and definitely it has some momentum. So it has increased its momentum. Sometimes maybe another example could be you have a ball which is probably, falling down, and then it hits some slushy surface, some mud, some soil, some sand, and it sinks in it. Yes, it did have some momentum before, and it decelerates and comes to a halt. It comes to rest. Here the momentum has decreased. Definitely momentum has decreased. Another example could be maybe there was a ball which was already moving in a particular direction, and maybe it happens to hit some surface over here. So after colliding with it, it reflects, it rebounds and goes over here with a new momentum P prime. So again, the momentum has changed, the direction and even the magnitude. So all these places, momentum has changed. And the way to change a momentum, how do you do that? By applying a force. You slap someone. Obviously, momentum has changed. Your hand and the person's. You slap someone, right? You kick a ball. Again, momentum has changed. You turn something. Again, the momentum of that body which was moving, so sorry guys, has changed its direction. Definitely. So, this momentum change is given a new name. It is called as impulse. The amount by which the momentum changes, is simply called as your impulse. It's simply called as your impulse. So, impulse is defined as nothing but defined as the change of momentum, Also, you will see after some time there is another way of defining it. So I will leave some space for it. Okay. You will see impulse is also defined in some other way. We'll come to that also in a bit. So for now, if I tell you, listen, our impulse, the symbol for that is J. It is change in momentum. That means it is delta P. So momentum is a vector, change in momentum is a vector. So impulse is also a vector quantity. So very, very important to see, it's a vector in the direction of the change, of momentum, This is very interesting to also see. Change is always final minus initial. So say for example's sake, maybe I was initially going like this, then finally I end up going maybe like this. This is my final direction. Because I've changed, obviously momentum has changed, so there is an impulse on that body. Impulse is final minus initial, it's a vector subtraction. So if I show the final momentum like this, the final momentum like this. Negative of the initial will be exactly opposite. So this probably would be negative of initial. This would be basically final momentum. Why negative? Because you can see minus pi. So vector subtraction is like vector addition of a negative vector. So then this thing over here, this thing what you see over here is basically your impulse, which is basically your J. This thing is basically your impulse. So you need to perform vector subtraction. Keep that in mind. You need to perform vector subtraction. If you ask me what is the unit of it, what is the unit of momentum or impulse or change, it will be the same thing. So it is still going to be kg meter per second or gram centimeter per second. That is the answer for it. Is this absolutely clear? Everybody with me? So impulse is just change in momentum, final minus initial momentum. That's how we define it. Understood? Clear-o. Very good. Some books use the symbol capital I. It's okay. Don't get confused. It's just a symbol. You can call, somebody might call you Pandu, somebody will call you Laddu. Your name will be something else. That's okay. It's just a pet name. It's just a alphabet. So don't get scared by it. Now, alternatively, I have another theory using Newton's law, Newton's laws of motion. We know any force which acts on a body, basically is responsible for its momentum change, and that is rate of change of momentum. That was your Newton's laws of motion. I will take dt on this side and see what exactly happens. So therefore, the change in the momentum, a small change, will be nothing but force into dt. I have an idea now. Let me integrate both sides. So integration of force with respect to time, maybe from t1 to t2. Over here on the left hand side, integration of dp, maybe from p1 to basically p2. Integration of dp is p, so substitute p2 first and then p1. So it will be p2 minus p1. p2 is final, p1 is initial, so it is nothing but change in momentum. But wait a minute, I know what is change in momentum. It is nothing but your impulse, guys. Change in momentum is nothing but your impulse. So impulse is alternatively written down, the same thing carries forward. Impulse is also alternatively written down as integration from some one time to another time, force with respect to time integration. Force with respect to time integration from these limits. Now, whenever I see integration, which characteristic of the graph rings a bell? Is it like the volume? Is it like the perimeter? Is it like the slope? Is it like the tangent? Is it like the area? What comes to your mind whenever you think of integration with limits? Yes, my dear students, come on, put it up in the chat box quickly. Whenever you see integration, what comes to your mind? What comes to your mind? So let's say, oops, we have this particular graph like this maybe. Okay, yes, area under the curve. Very good, correcto. So imagine this is basically T1, maybe this is basically T2, then this particular area that you see is nothing but area under the curve is the definite integral. We know this. We have seen this in basic maths. Hence, this is also nothing but area under the force versus time graph. Area under the force versus time graph. What does area under force displacement graph give you? What does the area under force versus displacement graph give you? Area under force and displacement gives you work. Area under force and time gives you change in the momentum, which is also impulse. Keep that in mind. So think about it. If the force is large and the time interval is large, the area will be large, which means the impulse will be large. So which means impulse can be alternatively written down as it is the effect of force and time on a body. If a large force acts for a large time, this integration will be big. So you have given a large impulse. Imagine somebody gives you a small slap for a small time, small impulse, big slap, dhab karke. And when you're hitting also, your face is going along with your hand. Large force, large time of contact. Obviously large impulse. Tup like this, if it is like this, fraction of a second, very small impulse. Big thappad, big slap for a large interval of time. In slow motion only you are going like this. So that will be a big impulse. Is this clear? That's why it is the effect of force and time on a body. Effect of force on time on a body, which is basically area under the force time graph. Yes, absolutely. I hope this is very, very clear. Great, great. Now that you understood, impulse can be either calculated via this or it could be calculated via this. How about using impulse in some places, and then we'll start with some questions. Now, see, imagine you have been given a graph. Imagine you have been basically given a graph of force versus time, and the graph of force versus time is sometimes up, sometimes down, and then suddenly goes up. It is variable. It is a variable force. Like you can see, it is a variable force. But I want to find out what is the average force acting on it. I think there will be some average. If I average it out, what is the average force acting on it? So how to find that average force? So the logic goes like this. Since instantaneous force is nothing but derivative of the momentum with respect to time, therefore the average value, average force, what is the symbol for that? You put the force, put triangular brackets. Do you remember this? Triangular brackets means average. If I put, P and this average momentum, V and this average velocity, A and this average acceleration. So whenever I put triangular brackets, it means average of the quantity inside of it. So average force will be what, guys? Can you guys guess it now? Very easy. Instantaneous velocity dx by dt. Average velocity delta x by delta t. Instantaneous acceleration dv by dt. Average acceleration delta v by delta t. So the d becomes large. That means you take a decent interval of time. So it will be nothing but delta t, and here you will have delta p. Oh, wait a minute. I know what is delta p. Delta p is impulse. Delta p is nothing but impulse. So basically it will be nothing but the impulse divided by our time interval. So this impulse is also, or I can say, or area under f versus time graph, one and the same thing. So that will give me the value of the average force. So you find the area under this particular graph. That area is nothing but your impulse, and divided by the time interval where you are calculating that particular average. That's it. That will give me the average value of that force. Is this very, very clear? Everybody with me on this? Absolutely. Okay, shall we do some questions now? Okay, so average force, impulse, defined in two different ways. There is one more addition. Impulse is force and times multiplication. Force is measured in Newton, time is measured in second. So I get another unit. Instead of kg meter per second or gram meter per second, centimeter per second, I can also write it as what, guys? Force and times multiplication. That means Newton second. So Newton second also becomes the unit of impulse. Newton into second also becomes the unit of impulse. So let's start with some questions. Here it comes. First question. A ball of mass m moving at v speed rebounds with same speed after bouncing. Find the impulse magnitude on the ball. Find the impulse on the ball. Let's try to visualize this scenario. A ball was going, it hits a surface and rebounds with the same speed. So let's assume that the ball was going like this, mass is m, velocity is v, and now it is hitting some surface maybe over here, and after the rebound or the bouncing action, it is coming back with the same speed. So in this process, 100% momentum has changed. So there will be an impulse acting on it. So that impulse, oh by the way, we should choose some direction as positive. So let me choose the right hand side as the positive direction. There is no harm in choosing left, but you need to choose something, right? So impulse will be nothing but final minus initial momentum. Final minus initial momentum. If you look at the final momentum, it is negative mv. Why? It's going towards the left side, so vector, so be careful. Negative mv. Negative mv. Initial momentum, if you see, it is going to be positive mv because it is going towards the positive side. So that's it, guys. So one is negative mv, other is positive mv. So what will happen? They will not cancel and give you 0, wrong. Rather, it will become minus 2 mv. So a lot of people give the answer as 0. They just write mv minus mv. Be careful, it is direction sensitive. So it is minus 2 mv, but they have asked you the magnitude of the impulse. So the magnitude of that impulse will be just 2 mv. If somebody asks me the direction, I will look at the negative sign. Immediately it will click, since the right side was positive for me, so the negative side is this way. So on the ball, the impulse will be this way. So the negative says the impulse as shown acts towards the left side in this situation shown. Acts towards the left as shown in the diagram. Is this absolutely clear? Magnitude and the direction, both we can get, but here in the question only magnitude was asked, but I gave you that extra piece of information also. Shall we proceed, my dear students, to the next question? Very good, 2 MV. Yes, Jasmine. Yes, Madhumati. Yes, Krishna. Yes, Pratibha. Correct. Keep answering, guys. I want everybody's answers in the chat box. All right. Now, let's take another situation. Let's take another situation, and here is the situation, guys. Say for example, we write it like this. A ball of 2 kg mass moving at 3 meters per second deflects by 90 degrees and moves at 4 meters per second in 0.4 or let's say 0.5 seconds. Find number 1, the impulse and its direction. The second thing, the average force acting on it. Find the average force also acting on it. Let's have a look. Let's draw a diagram. ball is going at a speed of 3. The ball's mass is 2 kg. So the initial momentum of yours will be towards the right hand side, or you can take any direction. There is nothing like you have to take right only. So I'll just show 3 meters per second over here. This is 2 kg. So the initial momentum will be 2 threes are basically 6 kg meter per second. Okay. Final momentum turns by 90. Whether you want to take it up or down, it's completely up to you. I just want to find the relative direction and just the magnitude. Okay, let's just say that it deflects down. There is nothing wrong in taking it up also. I'm just interested more in the magnitude and the relative directions. So the final momentum will be mass into the final speed. So it will be basically 8 kg meter per second. But we are being asked what is the impulse first. So it's a two-dimensional problem. Can you see that? It is a two-dimensional problem. So it is a two-dimensional problem. It's not going to work in just plus minus. You have to be careful with I cap, J cap, basically, the X and Y components as well. So if you look at the initial momentum and final momentum, they are in two different directions. So impulse being final momentum minus our initial momentum. What would our final momentum be? It's like this. Usually we take right hand side as positive X, upwards as positive Y. So can you not see final is negative J cap direction? So it is minus 8 J cap, guys. Everybody with me? Minus. What is initial momentum? It is along X axis, so plus I cap. So it is basically 6 I cap, guys. Oh, so the answer is minus 6 I cap minus 8 J cap. That is what our impulse is going to be. That is what our impulse is going to be vectorially. But if you talk magnitude wise, then you just have to take the components, square it and add and put it under the root. So this will just become 6 square 36, 8 square 64, 64 plus 36 100. Root of 100 is basically 10. So 10 kg meter per second is the magnitude of that particular impulse. Is the magnitude of that particular impulse. Everybody crystal clear about this? Yes, it's a two-dimensional problem. Now, what about the direction? We can easily show this vector minus 6 I cap. Okay, so minus 6 I cap will be left side. Minus 8 J cap will be basically like this, slightly longer. This will be minus 8 J cap. So naturally, our vector will be like this. This is our impulse. This length is 6 units. This length is basically 8 units. So if you want to measure this angle theta, tan theta will be 6 by 8, which is 3 by 4. Therefore, theta will be nothing but 37 degrees. So it is going 37 degrees with the horizontal. That's the direction of the impulse. You can measure the angle with respect to any other side also or any other direction. But I've just measured it with respect to X axis. You can measure it with Y axis, then it will be 53 degree. Is this clear? Absolutely. Okay. Now you might be wondering, sir, how do I know whether it is with horizontal or vertical? See, it will be given in the question. In this question, I didn't give you anything much. Find its direction. I give a vague question. You will see the options. You will see the question. Is it with horizontal? Is it with vertical? What is the direction actually? So I'm just showing you the concept over here, showing you how to do it. That's it. Once you get it, no matter whether it is going like this or like this, instead of going down, if it is going up or left or right, you will be able to solve the question. Yep. Is this clear? The last thing which is remaining is the average force, and the average force value, remember, is always the impulse by the time interval. The impulse magnitude was 10 and the time was 0.5. So therefore, the average force 0.5 is 1 by 2, 2 goes up, it will become 20 Newton. So 20 Newton is the average force acting on it. Everyone clear till this point? Understood? Shall we go ahead to the next question? Okay, let's go then. Let's go. Here you have been given force versus time graph. Okay, some points are marked in this graph. This is in Newton, this is in seconds. The questions are as follows. For 10 seconds, find, find number 1, the total impulse, number 2, the average force value, These are the two things I want you guys to find out. Clearly the force is changing with time, it is not constant, so you have to first find impulse and then you have to find what is that constant average value which you can replace that variable force with. Think carefully guys, what are you going to do? Okay, remember total impulse, if I have to calculate, I have to just measure the area under the graph. So if I have to measure the area under the graph, that means this particular thing and basically this particular thing. If you measure this area which is on the top, it will be nothing but half base, which is basically 8, into basically height, which is 7. 8 by 2 is basically 4. 7 4s are 28. Just keep it over there as it is. Same thing, do it for this particular part. Measure this area, it's a triangle, so half. Base is basically just 2 units. Height is basically 5 units, but it is below, so it is negative, which means 2 cancels and it will just become minus 25. So when you end up measuring the total impulse, which is area under our force versus time graph, please mind that 28 should not be added with 5, rather it will be subtracted. Basically you are adding minus 5, because areas which are below are negative, areas which are on the top are positive. Hence the answer will be 23 Newton second or kg meter per second. That is the first answer. Is this clear? Lot of people I have seen, they write the answer as 33. That is wrong, because then you have missed the negative sign here. If you miss the negative sign here, don't worry, the paper checker won't miss it, they will give you a negative mark over there. Talking about the average force. Average force is the impulse by the time interval. Impulse was 23. The time interval was 10 seconds. Hence the average force is 2.3 Newton. That's it. We have got the answer. 2.3 Newton. So easy it is to solve these questions when you know the theory. Or else you will be like, sir, how to find average, sir? Is it like, sir, I feel 3.5, sir. So 7, no, half of it, 3.5. No, it is not like that. You have to know the formulas. That's it. You'll get the answer. Okay. Let's go to the next question, guys, coming up on your screen. This might involve a little bit of integration, so be ready for it. If the force on a body is given by F is equal to 6t square for 0.5 seconds, find the impulse and average force. Find the impulse as well as the average force. Let's see how many of you can get this right. Find the impulse as well as the average force acting on it. The moment force is given as a function of time, you should be reminded of this formula, integration. Graph is given, find area. It is not given, you have to integrate. So integrate force with time, that gives you basically impulse. Okay, let's try that out. Impulse is nothing but integration of force with time from T1 to T2. If you notice, our force is 6t square, 6 is a constant, goes outside, dt is there. Initial time 0, final time 0.5 seconds. What is the integration of t square? It is basically t cube by 3, put the limits 0 and 0.5. Well, 6 and 3 cancels, it will just become 2 and you will just have t cube over here. But instead of t cube, what you should have is 0.5 first. So 0.5 cube minus 0 cube. That is what it should be. Substitute 0.5, then substitute 0. 6 and 3 cancelled, became 2. So this will become then 2 into 0.5 is half. So half cube is basically 1 by 8 and this is just 0. 0 cube is 0. So 2 into 1 by 8 is 1 by 4. So 1 by 4 is basically 0.25. So the impulse acting on it is 0.25 Newton second. Just check it. How many of you got it? Very good. Impulse is 0.25, 1/4. Yes, Pratibha, Krishna. Perfecto. Now talking about the average force. What is the average force? By definition, impulse by time or area under force versus time or integration of force time divided by that time interval. Impulse was 0.25. The time interval is 0.5. Obviously, this is exactly half, which is nothing but saying it is 0.5 seconds. So yes, it is, sorry, not seconds, newtons. So 0.5 Newton is our average force. 0.5 Newton is our average force. Is that clear? Shall we go to the next? Shall we go to the next? Everyone? Okay. Okay. So let's go. Let's go. Here is an example where two different balls, A and B, same mass, they are having same mass and they both are basically dropped. So what happens is both of them come down by some height till here, and over here they encounter a surface like this. Now after this, what happens is this ball stops here, this ball goes deep inside and it stops. Maybe this is little bit hard surface, this is soft surface. So the surface over here, it's little bit hard. So this is hard surface relatively. This is relatively a soft surface, so it sinks inside it a little bit longer time. Can you compare the impulses? Impulse on A versus impulse on B when it hits the ground. So when the impulse by the ground, on that particular ball, who will be more, who will be less? Let's see if you can get it. Who will be more and who will be less? Hard surface or soft surface? Where do you think the impulse will be more? Where do you think the impulse will be less? What do you guys think? Is A more or B more or equal, or they can't be set? Same mass, drop together, same height, right? So they both sink, but by different amounts. One retards quickly, the other retards slowly. What do you think is the correct answer about the impulse? Many of you might think, sir, obviously hard surface will give more impulse. It's hard, right? So more impulse. Soft will give less impulse. Is that what you thought? Yeah, most of you will think like that. But let me tell you, that is not the answer. The correct answer to this question is both of them are equal. I know it sounds strange, but it is true. I'll tell you why. If you calculate the impulse for A, the final velocity is 0. Here it will have some velocity, let's say v. So impulse is final momentum minus initial momentum, 0 minus mv. For this guy, final velocity is 0. This ball will also strike with the same speed, no? Same height, same mass, same gravity, both are dropped. So this will be also 0 minus mv. So 0 minus mv, 0 minus mv, which means the same. Hence, impulses are actually the same. Yeah, they will be equal. It feels very unrealistic, right? So it is not more or less, it is actually equal. But I know you guys are feeling that, no sir, something is not clicking, I'm not getting the feel of it. So I'll tell you what is the hurdle over here. The hurdle is, you are feeling hard surface gives more impulse because it will tuck, it will stop. Actually, here what happens is the time interval is less. Here the time for slowing down is more. And remember, impulse is force into time. Impulse is nothing but force into time, because force was impulse by time. So force into the time. Here also, force into the time. Because in this case the time was more, in this case the time was less, naturally the force here will be more, the force here will be less, because at the end of the day their product should be equal. Impulse is force into time. So here you will experience a large force, here you will experience a small force which acts for a longer time, which ends up giving the same change of momentum. So the forces are different, impulses are not. So that's why I said over here also, impulse is the effect of force as well as time. So even though the ball slowed down aram se very slowly in the second scenario, in the situation B, force was less but more time. And in the first case, case A, it stopped immediately. Force was large but time was less. So the impulse ended up being the same. Is that clear now? Yeah. So in fact, that brings us to something called as impulsive force. So look at this graph. And this one over here. This is force, this is time, this is force, this is time. Imagine the graph goes like this. The time is small, but this is a large force. It is a large force. Here, you end up measuring the area, and this is that area under that graph. This is that area under the graph. In the second scenario, what happens is the force is just like this and then goes down over here. If you measure the area, this would be the area under that graph. That's it. Here you have a small force for a large time. This was the situation of B. This was the situation of A. A, it stopped easily. B, it stopped slowly. Large time, small force. Here it was small time, large force. But the area was the same. Impulse was the same. So area, basically impulse was basically the same in both the cases. In such cases, I will say this force is impulsive in nature. This force is said to be impulsive. Whereas this force here is said to be non-impulsive in nature. Non-impulsive force. Some people are said to be very impulsive. Have you heard of this? This person, sir, you know, my friend is very impulsive. If you tell him, hey, today what is your hair? It's not looking good. Suddenly that person becomes angry. Hey, what are you saying? Suddenly, you hype up, you change your mood in a very short time. So that is impulsive. So if you are able to change the forces by large amounts in a very small time, such forces are impulsive. Like you getting slapped, large force, small time. Bat hitting the ball, large force, small time. A car colliding with a truck, large force, small time. A ball hitting another ball in a carom or maybe pool table. So large force, small time of contact. Those are impulsive. Non-impulsive, you are basically, imagine on a trampoline, a rubber sheet. You jump and you fall on the trampoline. Very nicely and slowly the trampoline absorbs energy and then slowly releases it. It is not sudden. If you fall on a floor, that's a sudden force. Your legs will get broken. But on a trampoline, slow absorption of energy and release, slow changes in the momentum, not so much force. So guys, non-impulsive. You take a spring and compress it. The spring slowly compresses, stops, and then releases the energy. Non-impulsive. Gravitational force, most of the times non-impulsive, guys. I mean, you release something, slowly the gravity will pull that object and increase the speed. But the same thing, a bat, thuk, within 1 second, fraction of a second, it will give that velocity. Gravity, power fellow, takes long time to give that, momentum. So that is the meaning of impulsive versus non-impulsive. Is the difference very, very clear, my dear students? What's impulsive force and non-impulsive force? Okay, great. Now that we are done till this point, let's go to the main parameter of this chapter, main law of this chapter, which is nothing but your law of conservation, of momentum. Law of conservation of basically momentum. What does this law say? If the net external force on a system, is 0, then what happens? The total momentum is basically conserved. The total momentum is basically going to be conserved. This is the law of conservation of momentum. Also, let me mention, internal forces don't matter. Internal forces, even if present, they don't matter at all. And talking about mechanical energy may or may not be conserved. Mechanical energy may or may not be conserved. So if you write it in formula wise, it will look like this. This statement, if net external force is basically 0, then the total momentum is conserved. That means the total momentum of that system will remain constant. That is basically your law of conservation of momentum, not energy. Law of conservation of momentum. Energy, the rule was completely different. If you remember mechanical energy, work per energy chapter, mechanical energy is conserved when evil forces like tension, friction, viscous force, they are not doing work, they are silent, they are not doing anything. Then you can say kinetic energy plus potential energy before and later is the same, they won't change. But here the criteria is only different. If the force externally net is 0, then the momentum is basically going to be conserved. Okay. Yes, Prince Nia, this will be also available as recorded because all the live classes get recorded as well on YouTube. That's how YouTube works. Let's take examples of this to understand what exactly is happening. Say for example, there is a 2 kg mass which is moving at 4 meters per second, and then there is another 1 kg mass which is probably moving at 2 meters per second. Okay, because this is moving slowly, this is moving fast, eventually they will hit. Imagine in this process these balls end up sticking each other. They stick to each other, they stick and move together with one common velocity. And I want to find what is that velocity. I want to find what that velocity is. Let's see whether we can use this principle or not in this situation. If the net external force is 0, then the momentum is conserved. Tell me, for this particular system, if I take this as a system, is there any force coming from outside? Is there somebody saying for 2 kg, hey listen, you accelerate, hey listen, 1 kg, you decelerate? From outside, nothing. So 100% external force is not there. It's 0. You might be wondering, sir, wait a minute, sir, they will collide. No, sir. When they collide, there is force. No, sir. Yes, there is force. But will it matter? Think about it and answer in the chat box. Will it matter? Yes or no? Definitely not. You know why? Because it is internal. So, very, very important. The collision force is internal in nature. Is basically internal in nature. So, doesn't matter at all. So, don't worry about it. Oh, so momentum is conserved. So, therefore, the total momentum of the system is going to be constant. So, I can conserve the momentum. What is the momentum before versus what is the momentum afterwards? Before, it is mass into velocity plus mass into velocity. So, 1 into 2. Finally, both of them are together. 2 plus 1 will become 3 kg because they stick together. So 3 into V. Oh, that's it. Let's see what happens on the left hand side. 2 4s are 8, 1 2s are 2. So 8 plus 2 is basically 10, guys. And on the right hand side, we just have 3V. So what will be our velocity? It will be 10 by 3 meters per second. That is the answer. 10 by 3 meters per second. Is this absolutely clear? NEET 2026 from Kerala. Hi Fawaz, welcome aboard. Now I want you to see one very interesting thing over here. After finding this velocity to be 10 by 3 meters per second, let's do one simple calculation. Can we find what is the initial mechanical energy? It is actually in the kinetic form. So it is half mass into V square plus half mass into V square. 2 cancels, 4 square 16. 2 square is 4, 4 by 2 is 2. So it is basically 18 joules. Can you see that? That is the energy before the collision happened. Let's calculate the final energy also. Half, it's now a combined mass. The speed is basically 10 by 3, which we just figured it out. Okay, so half into 3 into 100 by 3 square, 3 and 3 cancels. So this 2 goes with this as 50. So I'll get it as 50 by 3. Is that right, everyone? I'll just get it as 50 by 3. Now what is 50 by 3? And you compare 18. Are they going to be the same? 50 by 3 and 18, guys? No, right? It will be basically 16.67 joules. Definitely it has reduced. Definitely it's lesser than the initial quantity. So you might be wondering, where did that 1.33 joules go? Where did that 1.33 joules go? Basically it has been lost. So therefore there is an energy loss in this process. Energy loss, which is basically 18 minus 16.67 joules. Is that clear, my dear warriors? Everybody? Yeah, so the energies are not equal, so it will be almost like 1.33 joules. Yes, 1.33 joules of energy is lost. Yes, I'll definitely drink water. Thank you for reminding me. Let me just complete this discussion. Thank you for reminding us. Everyone understood? So this is what I meant by this statement. Mechanical energy may or may not be conserved. Internal forces like the collision force didn't even matter. Doesn't matter. The total momentum will always be conserved. Cool? So I'll give you a question and then I'll have some water. Okay? So try out this question now. Try out this question. Imagine there is a Pandu on a roller skateboard like this. He's holding a gun and he shoots that gun. The total mass of this system is, let's say, 60 kg, whole thing together. A small bullet of just, let's say, 100 grams is shot with a velocity of maybe 200 meters per second. Question is, find the recoil speed of Pandu. Find the recoil speed of Pandu. Pandu is on a smooth surface. Recoil means when you throw something, by Newton's third law, you will feel a reaction and you will move behind. That motion which is like backward against what you throw is called as the recoil. So when you are holding a gun and you shoot, the gun recoils, okay, because the bullet goes ahead. So that is called as recoil velocity. So try to figure out what is the recoil speed of Pandu plus the roller skate. Chalo, figure this out. Meanwhile, I'll just drink water and come. Okay, so guys, did you figure it out? What is it? If you take the entire thing, Pandu plus the skateboard plus the gun plus the bullet as your system. So this is our system. You will see there is no net external force acting on the thing. In fact, the gunpowder which will explode, that will be an internal force within the system. It will not matter for the total system's momentum. So definitely I can say the initial momentum is equal to the final momentum. Initially everything will be at rest. Pandu is holding the gun. He has not yet shot. Everything is at rest. So if everything is at rest, so it is 0, right? Because everything is going to be at rest. After shooting, the bullet of mass 100 gram, which is 0.1 kg, gets a velocity of 200 meters per second. So that's the momentum of the particular bullet. Similarly, even the Pandu plus the skateboard of mass 60 kg will get a recoil velocity of v meters per second, but do not forget this will be in the opposite direction, so minus. Remember, the recoil will definitely happen like this, not in the same direction. Momentum is a vector quantity, so that's why here. So this is the recoil of that Pandu skateboard system. That's it. So bring this guy over here. So 60 into v is 200 into 0.1, which is 20. So therefore, velocity will be 1 by 3 meters per second, which is 0.33. Negligible. Negligible. Got it? It is negligible. Now you might be wondering, sir, will this matter? Yes. How to reduce it? Should it be more? Should it be less? Well, I think it should be less as possible, because imagine Pandu shoots a bullet and he only flies off behind. Then what kind of system is that, right? So that should not happen. So when you shoot a bullet, you should not move behind too much. So the recoil speed should be less. In this case, it is decent only, it's not much. So it's okay. If you want to make it further less, what you should do is make the gun heavy. If you make the gun heavy, mass will be heavier, which means what will happen over here, when you take this on the other side, right? This 60 kg, if it is 100 kg, imagine this is 100, this will become even less. So a more heavy gun will have a less recoil speed. If you have a very light gun made of plastic, if you shoot the bullet will go this side, the gun will go that side with your hand, or it will hit your face only. So that's why the guns are very, very heavy. Got it, my dear students? Everyone? Awesome. Beautiful question on recoil and conservation of momentum. Let's go to the next question. Now this question will be involving some kind of 2 dimension. Okay, so here it is. There is a bomb of mass, let's say 4m, or let's say 5m at rest. M and 2m fragments after explosion. So this 5m mass, right? It breaks into 3 parts. One part is m, other part is 2m. Naturally, the third part will be 3m. After explosion, move in perpendicular directions with a speed of 2v and v. Question is, find the speed of the third fragment. Find the speed of the third fragment. See if you are able to visualize this question. Let me draw it for you. There is this bomb of mass 5m. This is before the explosion. Everything is quiet. Everything is at rest. Now what happens? There is one fragment of mass m, another fragment of mass 2m. This guy goes with 2v speed. This guy goes with v speed in perpendicular directions. Approximately speaking, the remaining fragment of 3m will obviously not go like this. By common sense, you know, if one goes here, one goes here, because the momentum has to be conserved, I feel approximately it will go over here. Let's say I call it u, and I have to find how much this u is. Is this part clear? Are you able to visualize this? Okay. Yes, that's the reason why army guns are heavy, and those cannons If you have seen the olden days, they used to use cannons and they put balls in it. That ball is only so heavy. It has to go with so much speed, so large distance. That's why the cannon itself is so heavy that it does not move much, has very little recoil. Happy Navratri, Sarvana. Nice to see you back over here on the channel. Okay. Now, I know one thing. Initial momentum and final momentum both will be conserved. So the total initial momentum will be the total final momentum. It has to be conserved. Externally, there is no force. If you see whatever is that internal force of that explosion, that internal force of explosion will not matter, because only external forces matter. Only external forces matter. Explosion force will not at all matter. Initially, what is the momentum? You can clearly see it is at rest, so 0. Final momentum, if you ask me, it is the momentum of the first particle plus the second particle plus the third particle. Oh, I know this and this. I think finding this will give me the velocity. So I have an idea. P3 vector, won't it be P1 vector plus P2 vector but with a negative sign? Just take these two on this side, it will become negative. So this is the momentum of the third mass, but I want speed. I don't want the vector, I want the speed. So I think I'll just find the magnitude. So the magnitude of P3 will be, since both of them are perpendicular, can't I say it will be root of P1 square plus P2 square? This minus sign won't come now because I'm only interested in the magnitude. I'm only interested in the magnitude because both of them are perpendicular. So what will happen? X square plus y square will give me the resultant. Is this clear? This is the most critical step of the problem. How P1 vector and P2 vector resultant is P1 square plus P2 square. Okay, so this is very important because they both were perpendicular to each other. Very crucial. That's why their resultant will be root of P1 square plus P2 square. What is the third mass's momentum? Mass into velocity. So 3m into u is equal to, what is the first mass's momentum? It is m into 2v square plus second mass 2m into v square. I can see the same thing coming 2 times. So it will become 2mv outside and you will have 1 plus 1, which is root 2, which is nothing but root 2. Okay. Now this m and this m will also cancel. So u will become 2v divided by 3. 3 goes below. 1 plus 1 is root 2. So v root 2 into 2 by 3. That is the speed. So the speed is 2 root 2v whole thing divided by 3. That is the answer. Got it? How to solve these questions? These questions are again very common in your NEET examination. You will find so many such examples. You will find so many such examples of such things happening over there. Clearo? Understood? Can we go ahead? Shall we go ahead, my dear warriors? Yep. Okay. Let's go. Let's go. So this is also done. This is also done. Recoil is also done. We just did a question on this. Okay. Now, let's do another example. Let's do another example. If Pandu and Champa are, Pandu's mass 60 kg, Champa's mass 40 kg, are floating in space at with no relative motion, floating in space with no relative motion, then find the speed of Pandu if Champa attracts him and move with a relative speed of 10 meters per second. Amazing question, guys, this is. They start moving towards each other with a relative speed of 10 meters per second. So what is the speed of Pandu? Now, why is Champa attracting Pandu? That is none of our business. But it is not that attraction what you are thinking about. It is some attraction. Maybe Champa had a magnet in her pocket and then Champa is like, hey, Pandu, magnet is removed. Pandu also removes the magnet and these magnets start attracting each other and then they start coming closer and closer. Is that clear, everyone? What is exactly happening in this? So if you look at the situation before versus situation afterwards, so let's say this is our Pandu and this is our Champa. Both of them were initially at no relative motion. Afterwards, what happens is maybe Pandu and Champa, they both begin to attract each other and they are moving now towards each other. They are moving towards each other. There is a relative speed. Let's say Pandu's speed is V1. Let's say Champa's speed is basically V2. Obviously, if you take this entire thing as a system, then there is no net external force. There is no net external force. Even if there is any force which is there of attraction, this attraction is going to be internal. This is going to be basically internal force. This is going to be internal force. So don't worry about that attractive force because for the Pandu-Champa system, it is internal force. So hence momentum is conserved, I say. So the total momentum initially is the total momentum finally. If you have been noticing in all the problems, I have been drawing two diagrams. Before, after. Before, after, here it was very easy, so I didn't draw. Here also, before, after. Here also, you can see before and after because this gives me clarity of what is exactly happening in it. Okay. So initially, both Pandu Champa were at rest, no relative motion, so 0. Finally, this Pandu going towards the right, so Pandu's mass 60, right? So 60 into V1. Champa's mass 40, so 40 into V2, but be careful, this is negative. Why is this negative? They are going in the opposite direction and momentum is a vector quantity, my dear students. So that's why that minus sign. So bring this somewhere over here. So 40 V2 will be 60 V1. Therefore, this will be 2 times V2 will be 3 times V1. Then I think, sir, I don't know V2. How do I find V1? Because the question says find the velocity of Pandu, which is V1. Without V2, I can't find that. Don't worry, there is something given to us. Relative speed is 10. We have not even used that piece of information till now. When I say relative speed of Pandu Champa, both are going in opposite direction. Opposite symbol is cross. Tilt it, it becomes plus. So whenever speeds are opposite, you add it to get the relative speed. So therefore, can I say the relative speed is V1 plus V2? That means 10 is V1 plus V2. Therefore, V2 will be 10 minus V1. V2 will be 10 minus V1. So instead of V2, you will put 10 minus V1. Awesome. So this is 2 times is equal to 3 times of V1. So this will just become 20 minus 2V1 goes on the other side as plus 2V1 and this is 3V1. So this will make it 5 times of V1 is 20. Therefore, speed number 1 is 4 meters per second. If Champa's velocity was asked, no issues. Also, V2 will be 10 minus V1. V1 was 4. So it will be basically 6 meters per second. So this is for Champa, this is for Pandu. We have found both of them. Such an interesting question. Got it, guys? How to solve these kind of questions of relative velocity is also given, and then they conserve the momentum also in this process. They conserve the momentum also in this process. Such a beautiful, beautiful question. Great. Moving on to a tricky question now. Get ready. This is going to be a slightly tricky question. If this question comes, it will be one of the most tricky questions for NEET, and it can come, let me tell you. It has come in different ways previously in AIMS, etc. And the way things are going, we should expect a difficult paper for NEET 2025. Not trying to scare you, but NTA might just try to take revenge, you know, because of all the scam and all the revolt which happened. Anyways, we have to be prepared mentally. So, let's solve a question. Let's solve a question. See, imagine there is a mass M, and let's say there is a spring over here, and there is a spring over here like this. This is mass 2m, this is k. Everything is on a smooth surface. This is going with the speed of u. This is going with the speed of u. This thing is right now at rest. This mass goes and touches the spring. The moment it touches, the spring will start to compress. So the moment the spring begins to compress, spring will start pushing 2m and 2m will start to move. But this mass, because it is compressing the spring, it will slow down. So you will see these two masses will act like this. This mass is here, this mass is here. It will come with a constant speed. It will slow down and this will accelerate, and maybe it will go like that. So there comes a time when the spring is compressed while both are moving together. Spring is compressed while both are moving together by a maximum amount. So question is, find the max compression in the spring. Find the maximum compression in the spring. How do we solve this kind of question? Here, you need to visualize what exactly might be happening when the compression is maximum. Let's try to visualize that scenario. Let's try to visualize that particular scenario. So, probably it will happen somewhere here. When the compression is maximum, that means the spring is no longer compressing at that moment. It was moving like this end was moving like this, it was compressing. Maximum compression happened. After this, it begins to expand. So there was compression and then it stopped and then it began to expand. So can you comment something about the ends of the spring? If a spring is compressing, and then after that it begins to again expand. So when the maximum compression happens, what can you comment about the ends of the spring? Quickly put it up in the chat box. By gut feeling, what do you feel? By gut feeling. Compressing, stops and goes back. Between the two ends of the spring, what do you see? Compressing, 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 stops and then again starts expanding. At the maximum compression, both the ends of the spring stop relative to each other. The relative motion is zero. Do you agree with this? There is no relative motion between them. So hence, when the spring is compressed by a maximum amount, this is for max compression, I will say there is no relative motion. But does not mean there is no motion. No relative motion means the ends are not moving with respect to each other, but both of them can be together moving. Hence, this might have some speed. This will also have the same speed. This is the crux of the problem. The person who understands this, the next part is very, very simple. Yes. Is this clear? So this mass comes like this, close, stops and then goes. So when the maximum compression happens, there is no relative motion. That's it. After that, the spring begins to expand. So maximum compression, no relative motion, you can see that. And after that, the spring begins to elongate. Absolutely clear. Speeds will be there, but it will be same. Now, believe me, this is now a question on momentum conservation. If you think carefully, this entire thing is my system. Here also, this entire thing is my system. So conserve the momentum. Initial momentum is equal to the final momentum. You might be wondering, sir, spring force is there. Forget it. Spring is a part of the system. I've included the spring, which means it will become internal force. So will it matter? No. So what will you do? Forget about it. So the moment you forget about it, it becomes easy. Initial momentum is just mu. The other guy is at rest. Final momentum, mass into V. Spring has no mass, so plus 2m into V. So m cancels, so U will be V plus 2V, which is 3V. So therefore, V will be U by 3. Oh, we get the common velocity with which they move. Amazing. But then you'll be like, sir, that was not even the question. What did you find? The question was to find the compression. Oh, wait a minute. I need to find compression. So I might have to use something else. I remember energy conservation. Oh, yes. There was kinetic energy of the mass. Can you see that? There was kinetic energy of that mass initially. Nothing over here or the spring. That should be equal to the mass. Afterwards is also moving. This mass is also moving finally, and there is spring potential energy. So initial kinetic energy is kinetic energy of this guy, and the energy stored inside the spring. Is that absolutely clear? So what is the kinetic energy of that mass? It is half mu square is equal to kinetic energy of the mass later on. It is half m. The speed v is u by 3. So u square by 9 plus half 2m. Speed is again u by 3. So u square by 9 plus spring energy half k x square. A lot of things might get cancelled, like this half, this half, this half, and this half. So now what do I see? Mu square is over here. Start bringing these people over here. So guys, this will become minus mu square by 9 minus 2mu square by 9. This is going to be equal to this kx square. So this is minus 1, minus 2 will make it minus 3. Minus 3 by 9 is minus 1 by 3. So therefore, it will just become mu square minus mu square by 3. I hope you got it. Minus 1 minus 2 is minus 3. Minus 3 by 9 is minus 1 by 3. 1 minus 1 by 3 is 2 by 3. So therefore, I will get this as 2 by 3 mu square. In the right hand side, I still have my kx square over here. Kx square over here. So that's it. That's the last step now. K you bring it down. K you bring it down. So x square will become 2m by 3k and we will have u square. So x will be u root 2m by 3k. That's it. That is the answer. That's the max compression. I hope you loved the question. The challenging part was both of them move together, number one. Number two, you have to conserve the momentum also and you have to conserve the energy also. All the things were involved in this question. So that's why it is a brilliant question. Yeah, great. Now that we have studied these collisions till here, we have, or momentum conservation problem still here, we have the next task of studying the different types of collision. There are different types of collision bases on whether energy is lost or not lost, and whether it is more or whether it is less. So there are three different types of collision that we study. The first one is just called elastic collision. The second one is called partially inelastic. This is called perfectly inelastic collision. Now the word elastic means, it regains its shape and size after being deformed. The opposite of elastic is inelastic. The examples of elastic is a rubber band, or basically a spring. All these are elastic bodies. Some people are there, how much you tell them, study, even if you put them in the front of the desk, they will go and watch a movie or play a game. So their behavior is elastic. Their original state was to play the video game. Even if you put them in a classroom, even if a teacher is sitting in front, even if you throw them outside, they'll again come back inside and play the video game. So that is elastic behavior. Inelastic means, you ask them, okay, study, they'll sit and study. Okay, go play, they'll go outside. They deform very easily. That is inelastic behavior. Got it? Everybody clear? Yes. So that is how we have defined the different types of collision. To make you understand this, I have a simple solution over here. Maybe this one. Oh my God. Let's make it one-dimensional. Okay. Oops, I don't want so much data. Let's do it with this. That will be better. Okay. This red block and this blue block. I hope you can see that. I have given the red block a speed of 10, the blue block a speed of 5. And I will allow both of them to collide, and let's see what exactly happens. All right. Over here, there they go. And they go away from each other. Perfect. Let's reset. Let's give this guy also 10 speed and this guy also 10 speed. They both hit and they go back with the same speed. Do you see that? This kind of behavior where they come and go, without losing any energy. They come and go without losing any energy. This is called as elastic behavior. I won't hear any sound. There is no light. There is no heat. There is no energy loss. There is no deformation. Whatever energy was spent during the collision, it is regained back with the masses. There is no loss. It's faithful. So it's conserved. Energy is conserved. So elastic behavior. It regains its original shape and size, and it is as it is. It is elastic collision. I will now make it slightly inelastic. Observe what happens. Oh, it slowed down, guys. Did you see that? They hit. They slowed down. In fact, you can see it graphically also. Their velocities, it reduced. Their velocities have reduced. Can you see that? Initially and before, the speeds, if you compare, they have definitely reduced. If I make it more inelastic, then they will reduce even more. So kinetic energy lost is 470 joules. You make it even more inelastic, oh my God, losing so much of energy. You make it perfectly inelastic, totally inelastic. That's it. Thup, stopped, lost all the energy. They got stuck to each other. Amazing, right? And this works not only in opposite directions, but also in the same directions. So let's say, for example, let me give it a small speed, or maybe this is 0. This is very easy to visualize. Let me make it perfectly elastic, mainly basically elastic behavior. See, this will be at rest, this will come and hit it. It transferred all the energy to this. This is elastic behavior, perfectly elastic behavior. Let me make it slightly inelastic. It lost somewhat and it did not give it so much of energy. There is some loss of energy. You can see the energy lost during the collision is 58 point something joules. Before, there was no energy being lost. 0 joules of energy is lost. So I make it even more inelastic. That's it. They both go slowly. So many joules of energy is lost. I make it even more inelastic. Oh my God. See this. They are trying to move together. And there you go. This is perfect inelastic collision. This is a perfectly inelastic collision. Maximum energy is being lost during the collision. So cool, right? Isn't it? This also works, by the way, even in two-dimensional motion as well. So if I do two-dimensional motion, let me play this. Stick, slip, momentum diagram, play. Yes. Ooh, my God. Okay, 1 second. I don't want this. Where did it go? Explore 2D. Yes. 100% elastic behavior. Okay. This guy and this guy. We can change the speeds also. So cool. Hopefully they collide. Oh, they collided. Wow. So nice. This is elastic behavior, guys. Okay. Let's get it back. Reset. Can we get their masses to be equal so that I can easily see what is happening? Okay. Both are 50-50. Wow. So nice. This is elastic behavior. Okay. That is basically elastic behavior. Okay. Let's get it back. Let me make it slightly inelastic. There you go. Hits. Lost some bit of speed. It has lost some bit of speed. Okay. Let me make it even more inelastic. This is two-dimensional collision. Oh my God. Look at it. Lost so much of energy. Let me make it completely inelastic and see what happens. Ooh. Very good. So inelastic, perfect. Oh, there was 5% inelastic behavior. I can't make it perfectly inelastic for some reason. I don't know why. But maybe in the other diagram I can do that. But yeah, there is some bit of elasticity still left, 5%. I cannot go to 0% for some reason. Okay. Oh, I can increase the number of balls too. That is so cool. Imagine all of them coming and hitting somewhere like this with perfect elastic behavior. Wow, this is so cool. This is like a nice diagram where you can keep watching it endlessly. And what if I increase? Oh, I can't get it more than 4, unfortunately. And there you go. This is slightly inelastic behavior. Every collision is making them lose some energy. I can see eventually they will stop. So our day-to-day behavior is inelastic. You don't find elastic behavior of bodies which are colliding. Else, a car colliding with the truck, after collision also the car is moving, truck is also moving. That is inelastic actually in reality. So when the car collides with the truck loses energy, car loses energy, there is deformation, breaking of bonds, structure gets damaged, sound is there, light is there, heat is there. So energy is lost in reality. Is that right, everyone? I hope you loved this simulation. We'll come to this in a bit again. So in elastic behavior, the kinetic energy, or basically I will say there is no loss of energy. There is no loss of energy. Here I will say there is loss of energy. Here also there is loss, but this is the maximum possible loss. There is maximum loss of energy. If you write over here, the kinetic energy initially of the system will be the final kinetic energy of the system. Here if you write it, the initial kinetic energy will be definitely more than the final kinetic energy. Here also, basically the initial kinetic energy will be more than the final kinetic energy of the system. Just that the final will be much, much lower. In all of them, there is one thing which will still be conserved, and momentum. Momentum is still conserved. Please mind it. In all of them, in all these collisions, momentum is still conserved. Don't say momentum is not conserved here. Momentum is still conserved. Because energy being conserved or not conserved is none of my business for momentum. Okay, they are two separate things. They have two separate criteria. Examples of elastic behavior. Examples of elastic behavior is a proton colliding with another proton at molecular atomic level. That is a elastic behavior. The charges will come very close, stop, and again they will go. No energy is lost there, so that is the elastic behavior. Another example of inelastic behavior is your reality. If you basically an accident which happens, vehicles colliding, it is inelastic behavior. Or your day-to-day life, you throw a ball, it hits the wall but comes back with lesser speed. Perfectly inelastic behavior. Imagine they stick together after collision. They stick after collision. I have seen some funny reels and videos where a big fat person is running and one Chintu Mintu person is coming and they collide, and that's it. After that, that Chintu Mintu person has stuck to that person's body and both of them are running together. So that would be a perfectly inelastic collision. Or some bike fellow is going on his bike peacefully thinking about some champa, and then one car or some big bus or truck hits that person and both of them now are moving together. That is a perfectly inelastic collision. Got it, guys? Yep, everybody till this point? Very, very cool. Now there is one more parameter which defines how elastic that behavior is, and that parameter is nothing but called as coefficient of restitution. That parameter is 1 for perfectly elastic. For partially elastic or inelastic, it is less than 1 but more than 0, and that parameter exactly is equal to 0 for a completely inelastic collision. For a completely inelastic collision. This is how that parameter is. We'll come to that parameter in the next slide, don't worry. Graphically, if you draw the energy with time diagram, energy with time diagram, the diagram looks something like this. Initially it had something, it might lose something, but it regains back its original shape and size, so there is no loss. Here it had some kinetic energy, it deforms, it does not come back to its original shape and size, so there is definitely some loss. In the perfectly inelastic, it deforms and it never regains the shape, so there is definitely a loss, but this is maximum loss of energy. So here it recovers, here it partially recovers, here it never recovers, it loses maximum energy. Is this clear, everyone? Okay, awesome. Now what is this parameter E? What is this parameter E basically? So let's talk about something called as coefficient of restitution. Coefficient of restitution. So Newton in that particular era, okay, this is Newton in that particular era, 200-300 years back, what he did was he was playing with steel balls, not like you guys, very, very, religious student of science. He was playing with these balls, and basically he saw how these different balls behaved. First time he took steel balls, then he took marble balls, then he took iron balls, then he took wooden balls, and then he analyzed what is the motion before, after. Imagine, crazy, right? We wouldn't do that. Now, we will probably be using our thumb for what? Scrolling the reels. Yes, so our Newton that time was playing with balls. Amazing. So, he realized after playing with balls that there is a ratio which is constant, and that is the coefficient of restitution. The symbol for that is basically E. And he found that this coefficient of restitution is the relative speed of separation, after collision, and you measure the relative speed of approach before the collision. That's it. You measure these relative speeds, take the ratio, you get coefficient of restitution. So E is the relative speed after upon the relative speed before. That's it. As simple as that. It's a positive number always. Okay. That is your coefficient of restitution. Very, very straightforward. Yeah. Thank you for appreciating my diagram skills. Yes. I hope it looked like Newton. Just to give you an example of what this could look like. First example, imagine one guy is going with 2 meters per second. This guy is going with, let's say, 10 meters per second. After the collision, this guy's speed is 3 meters per second. This guy's speed is 1 meter per second. If you calculate E over here, what will it be? After and before. After is this. This is after collision. So can you see the relative speed will be 3 plus 1. Here, this is before, opposite direction, so the speeds will add. So 2 plus 10. So it will be 4 by 12, which is basically 1 by 3. So the coefficient of restitution is 1 by 3. Got it, everyone? Awesome. Similarly, my dear students, imagine one guy going with 7 meters per second, this guy going with 2 meters per second. After the collision, this guy's speed reduces to, let's say, 4 meters per second. This guy's speed increases to 5 meters per second. What is the coefficient of restitution in this case? This is after, this is before. So always after comes on the top. Both are moving in the same direction. Same means minus. Subtract these two. 5 minus 4. Same direction means minus. So 7 minus 2. 5 minus 4, 1. 7 minus 2, 5. So coefficient of restitution is 0.2. This is basically 0.33. All these are inelastic collisions. You can see that. So this is what coefficient of restitution is. In elastic collision, E is 1. That means approach and separation relatively is same. In a partially inelastic collision, approach is more, the separation is less because there is a loss. In perfectly inelastic collision, they approach but there is no separation. That's why E is 0, because the numerator is 0. They stick together after the collision. So that's why E is going to be 0. Yes. Got it, everyone? Clearo? Perfecto? Amazingo? Very good. So how about we take a break and we return after 20 minutes? Yes? So let's have our lunch. So this is our lunch. Some things are there. Some chapati is also there. It's very nice and hot. So time for a break. We will return. Okay. We'll return soon. Meanwhile, yeah, please like the video and subscribe. Okay. Welcome back, welcome back, welcome back. Yes, Matthew, I'm taking the complete chapter with questions, like you can see. So, join guys. By mistake, I think I had put the timer as hours instead of minutes. So that's what I was wondering. Why is it taking so long? Then I just realized I had set it up as 17 hours instead of, or 18 hours instead of, you know, 18 minutes. Welcome back, guys. Yep. So Shreyas Sir is back. Get ready, guys. All the students, welcome back to the channel. And before the lecture, we had just seen elastic, which is where no loss happens. Energy is conserved, E is 1. Partially inelastic, where energy is lost, E is less than 1. And when E is 0, maximum energy is lost during that collision. That is perfectly inelastic, where E is the restitution coefficient. It's the relative speed after the collision upon the relative speed before the collision while they approach each other. So let's start with some questions and see how do they come out to be. Yep. So here is the first question coming up on your screen. There is a 3 kg mass moving at 2 meters per second. There is a 1 kg mass which is at rest. After the collision, given that E is basically 0.5, question is find the speeds of the 3 kg as well as the 1 kg mass. Question is find the speeds of both the masses after the collision. Basically, if I assume this as V1, this as V2, I have to find both V1 and V2. Okay, so let's see how do we do it. E is given, then most likely I have to use it. That's the reason why it has been given only. So the value of the coefficient of restitution is the relative speed after the collision upon the relative speed before the collision. Since E is 0.5, that means it is basically half. Speed after the collision relatively, V1, V2, same direction. So this guy comes and hits this goes like this. This guy comes from here, hits like this, and they both go like that. So the 1 kg mass will be moving faster than the 3 kg mass. So V2 will be more. So hence, can I just say it is V2 minus V1? This is after the collision. Before the collision, one guy is at rest, the other guy is just coming towards it. The relative speed is just going to be 2 meters per second. 2 cancels. So 1 is basically V2 minus V1. If you look at this, you will be like, sir, we had to find both V1, V2, but this equation doesn't give me both. If I know this, I can find this. If I know this, I can find this. So how do I find the other given this scenario? Obviously, this is not sufficient for me. I need something else. Think, what do I need? Hi, Jasmine. Welcome back. Yeah. I need probably conservation of momentum. So let's conserve the momentum irrespective of what type of collision it is. Momentum is always going to be conserved. Initial momentum, mass into velocity. The other guy was at rest, so plus 0 is equal to mass into velocity, so 3v1 plus 1 multiplied by v2. Okay, 3 2s are nothing but 6 is 3v1 plus v2. I have another equation in v1, v2, so obviously we need to solve them. From here, I hope you can see v2 is 1 plus v1. Take v1 over here, 1 plus v1 is v2. So instead of v2, I'll just put 1 plus v1 and the remaining things as it is. So 3v1 is here and we have 6 over here. So 1 comes over here, 1 comes over here. So 6 minus 1, 3v1 plus v1 is basically 4v1. 6 minus 1 is 5. So v1 will be 5 by 4 meters per second, or basically 1.25, or basically 1.25 meters per second. That is the speed 1. Can I find speed too? Yes. Just use this equation. V2 will be 1 plus V1. V1 was 1.25. That means it will be 2.25 meters per second. That is the second answer. Got both of them. Got it? Hello Krishna, welcome back. Hi Ahmad. Yes, very good. So this is how I can find the final velocities given any scenario. Let's take up another example so that you guys are well versed with this. Okay. Let's take another example. So again the same question. After the collision, can you try to find the speeds of both these bodies which have been collided? These bodies are colliding elastically. That means E is 1. That is understood. So find their speeds. So we have to assume some direction. Maybe this guy is going here, going like this. You don't know what might happen. Maybe this guy after the collision might go like this. I'm just assuming this. This is velocity 1 and this is probably velocity 2. Just taken some random directions. Just assumed something. Let's see what happens now. Because it is elastic collision, E is definitely 1 in the next step. This is velocity after and this is velocity before. All this is, remember, relative velocity. Do not forget that. After the collision, the relative speed, both are going away. Opposite. Opposite means add. So it will be V1 plus V2. Here they are coming towards, again, opposite direction. So again add. So 4 plus 2. So therefore 4 plus 2 is 6. So 6 is equal to V1 plus V2. I can't do much because I have two unknown variables. I need one more equation to solve them. Which better other equation than conservation of momentum? So conserve the momentum and see what exactly happens. Initial momentum 2 into 4. This guy is going left side, so minus 4 into 2 is equal to. This is going left side, so minus 2v1. This is going right side, so plus 4v2. Is the sign making sense? Because directions do matter for momentum. Hi Tanuja, welcome aboard. Yeah, and thank you Krishna for the appreciation. We took some effort to put those thumbnails just for all of you because you also are bored seeing us in the same avatar again and again. So we thought we should have a different avatar, and that's why the Navratri avatar. Yes, so don't expect us to dress up like Santa Claus during Christmas, okay? Or maybe we can, I don't know, with some free gifts. This is going to cancel out, this is going to be 0. This is just going to be 4v2 minus 2v1 divided by 2. So you will get 0 is equal to 2 times v2 minus v1. Okay, now what do I do from this? What do I do from this? I will get v1 is basically 2 times of v2. When I get this v1 as 2 times of v2, substitute it over here. So 2 times of v2 plus v2 over here is basically 6. So 6 is basically 3 times of v2. Therefore v2, 6 by 3 is 2. So 2 meters per second. Once I get v2, we can easily find the v1 value, which is 2 times of 2 only. 2 times of 2, which is 4 meters per second. Now the best part is both the answers came out to be positive, which means just by coincidence, just by pure coincidence, I have assumed the correct directions. If by chance I got the answer as negative, which means the direction shown is not correct, it will move in this direction. That's what it means. Is this clear? Why we got positive answer? What it means? It's pure coincidence, pure luck, nothing else. Okay. Moving to the next question. This is also an amazing question, guys. Let's see if we can solve this. What happens? Somebody drops a ball of certain mass from some height h0, onto the ground. This is the ground. What happens is, after hitting the ground, because the ground itself has some coefficient of restitution, this ball will not go up so much, probably only goes till here before again trying to come down over here. Next instant, it will not go up so much, it will probably go only till here and again just come down back over here. And this continues, this journey, and you will see eventually maybe it, after nth collision, it will go till certain height and come back over here. So let's say this height is h1, this height is h2, and this process continues. This process continues, and after nth collision, the height is hn. We want to find what that height is. What is the height which the ball goes up after nth collision? Very interesting question. Just try to see this. I'll remove this, okay, and I will make the velocity 0 over here, or maybe I'll just throw it with some velocity. I'll keep it inelastic collision. You will see, I don't think gravity is there over here. After every collision, the speed is reducing. If gravity was there, it would not continuously go up. It will stop after some time. So definitely after every collision, the speed reduces. You can see, again it collides, again the speed reduces. So definitely we can say the height reached also keeps on reducing. Yeah, the height is reducing. Why? Because of E. And E is inelastic collision. That means energy is being lost in some way. When you drop a ball, thug, 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 thug. What is happening? You are hearing the sound energy. The floor might get heated up, heat energy. There might be some spark, light energy. Some deformation energy. So definitely some energy is lost. The restitution is given to us. So how do we figure this bit out? So what we do, first of all, is there any relationship between the heights and the speeds over here? I think there is. It will hit the ground with some speed v0. Then it rebounds with some speed, comes back with the same speed, let's say v1. Here it goes with a new speed which is even lesser. I call it v2. Similarly, after the nth collision, it goes up and it comes down with some new speed, basically vn. Is the height and the speed related? Yes, we know the maximum height and the speed formula. What's the maximum height and the speed formula? If you remember it correctly, it is nothing but height is speed square by 2g. Is that right? Height is speed square by 2g. So same way here also I can say height is nothing but v0 square by 2g. Same thing over here after the nth collision, hn is basically vn square by 2g. Is that making sense to all of you? Where did I get this from? I got this from vertical free fall motion. Vertical free fall motion theory. Maximum height is initial speed square by 2g. We have seen this over there in that particular chapter, right? So if you throw a ball up, maximum height reached is given by the speed square by 2g. Cool. So if I want to find this height, I need to know Vn. To find Vn, is there any relationship between the speeds? I think there is. I'll tell you how. If you look at E, for this collision, when it hits the first time and reverses, what you will notice is, after collision, the speed of separation between the surface and the ball is basically V1. It is going with speed V1 upwards. So speed with which it goes away relative to the ground surface is V1. The speed with which it approaches is basically V0. So technically speaking, V1 is nothing but E times of V0. Same logic, let's apply it for the next collision. Let's apply it for the next collision. It hits the ground with speed V1, but it rebounds with a slightly lesser speed. So after the collision, the separation velocity is V2. The approach velocity, it approaches with speed V1. So therefore, over here, V2 is E times of V1. But wait a minute, V1 was E times of V0. So it will be E times of V0. So it will become E square times of V0. That is what V2 will be. Now I can see a trend. V1 is E raised to 1 V0. V2 is E raised to 2 V0. V3 will be E raised to 3 V0. So definitely what will happen, similarly, Vn will be E raised to n times of V0. Is there a trend that you are seeing, guys? Second time collision speed is E raised to power 2 V0 and so on and so forth. So substituting it over here, height after the nth collision will be E raised to n V0 whole square by 2g. E raised to n raised to 2 will become E raised to 2n. Here what I get is nothing but V0 square, and at the bottom I get 2g. Why did I put it like this? V0 square by 2g is the old height. So basically I have h0 over here, and here I have E raised to 2n over here. So that is the height after the nth collision. We got the final answer, guys. We got the final answer right over here. The height after nth collision is the original height from which it was dropped into the coefficient of restitution raised to 2n. Coefficient of restitution raised to 2n. Everyone understood this? This is a very, very important question. Very important question. You should know this question and how to solve this. I have explained it very systematically. What did I do? The height and the speeds are related after everything because it is a vertical freefall motion given by speed square by 2g. After every time the speed reduces, so speed after upon speed before is e. Speed after upon before is e. So from this we got V1 is e times V0. This speed is e times of previous speed, but the previous speed was previous speed into e. So every time e gets multiplied. So after nth collision, e will be multiplied n times for that original speed with which it hits. Substitute in this height formula, I will get in terms of the original height. Cool? Evening star, Krishna, understood? Clear? Amazing, amazing, guys. Now, let's do a question in 2 dimensions. To find the relation between the angles of incidence and reflection from inelastic surface. Okay, from an inelastic surface. So what do I exactly mean by that? So just imagine there is a surface like this which is inelastic in nature. Coefficient of restitution is E. If I draw a normal to it, it will look like this. This is the normal drawn to it. Then what happens is there is a ball which hits the surface over here and it rebounds like this. Initial velocity is here, final velocity is over here, like this. So this is u, this is basically v, this is angle of reflection, this is angle of incidence. Question is, what is the relation between these angles in the given terms? Now, why is this useful? Is because whenever you play carom or anything like that, say over here, take this only. Just imagine this is like you are throwing something, maybe let's say there are two balls and maybe this guy is at rest over here. You are aiming over here and you want to take a shot. You want to make it go like this. You usually feel the angle of incidence is angle of reflection, but that's not really the case. That's what you will see. You take these shots like this on a pool table, etc. So always angle of incidence is not angle of reflection, and we can see that over here. Observe this carefully. Let me see if a grid can be shown somehow. Okay, grid. All right, observe this. I will shift the ball over here. I will throw the ball over here and I will make it inelastic collision. Observe this. It hits. I don't think the angle of incidence is angle of reflection. I don't think the angle of incidence is the angle of reflection. Just check this out. Again, I'm throwing it like this. See how it is going. No, it is not. If you want, let's do this again by making it more inelastic so the behavior is even more apparent. 100% the angle of incidence is not equal to angle of reflection. Unless I make it perfectly elastic, then it goes like this. Angle of incidence is equal to the angle of reflection. But the moment I make it inelastic, that's it. It is no longer, going to rebound with the same direction, same angle. So that is exactly what we want to try and do over here. Is this clear? I hope I made you visualize this through this particular animation. Okay. Now first things first, the velocity which you have, it has two components. This velocity which you have initially, if you see, this is the angle of incidence, guys. This is the angle of incidence. So this velocity will have two components. One will be u sine I and this will be u cos I. Similarly, why is this I, by the way? Because you can see if I draw a vertical like this, these two lines are parallel. This line is going in between. So this angle will be this angle. Okay. Now for that velocity, this is v. This will be one component. This will be one component. This is r. So this is v cos r and this is v sine of r. So these are the components of the velocities. I will need it for solving the problem. First of all, realize that when the ball strikes this surface, there will be a sudden impulse in this direction on the ball. This is on the ball. That means this has come because of a force acting on it for a small time. So there is an external force on the ball in the y direction. But the external force on the ball in the x direction is 0. Yes, there is an impulse here, but there is no impulse like this in the x direction, which means the momentum in x is conserved. Momentum in x is going to be what? Conserved. Oh, that makes my things little bit easy. In the x direction, the initial momentum will be mu sine I. Final momentum in the x direction will be mass into v sine r. Cancels. So u sine I is equal to v sine of r. Oh, perfect. Let me call this as equation number 1. This is one of the equation which I get by conserving momentum in x, because there is no force in x, impulse is there on this direction. Great. Now you'll be like, sir, what else can we do? We didn't even use E. Don't worry, we'll use E. We want to use E. But then the question is, there is relative separation, there is a relative approach. This is obviously relative separation after, this is relative approach before. Now you might be wondering, what is going to come on the top, what is going to come below? I have seen many people write, sir, afterwards the speed is V, before the speed is U, so it should be V by U. That is wrong, because the impulse was in this direction. That means this was the direction in which the ball collided. If you notice, the ball had two components of velocity. Nothing happened only to this, because there was nothing to hit it in this direction. So whatever hit it, whatever struck it, whatever collided, the collision happened in this direction. So why would you bother about the horizontal components here? Only take the components along the impulse. You will only take it along the impulse. So whenever you see such questions of 2 dimensions, always take the components in the direction in which the collision is actually happening. Is that clear? Yes. The NEET 2025 will be definitely difficult, is what I am assuming, than the previous years. I am not saying it will be like J Advanced or J, but it will be definitely difficult, because they don't want such high rank inflation. Lot of hangama happened. They don't want their name to be spoiled again. Think logically, go by human psychology. Yeah, so only the vertical component will come. So only take over here V cos R and over here U cos I. Rearranging, we get E times of U cos I is equal to V times of cos R. That is equation number 2. What I will do is now, I will divide equation number 1 with equation number 2. Equation number 1 with equation number 2. Observe what do you get. Here on the numerator you have U sin I, and here you have V sin R. In the denominator you have E times U cos I. Here you have V cos R. So this is what I get after dividing this and dividing this. U cancels, V cancels. Sin I by cos I. What is sin I by cos I, guys? It is nothing but tan I. So tan of I, E remains below, is equal to sin R by cos R. That is nothing but your tan of R. Further, if you rearrange, you will get E is equal to tan of I remains on the top, tan R just goes below. Now this is not something which you can ignore. You have to remember this. So the coefficient of restitution is tan I by tan R. The best part, it looks like Snell's law. It looks like Snell's law. Remember Snell's law in the refraction, ray optics, coefficient of refraction was sin I by sin R. First difference, this is not coefficient of refraction, this is restitution. Second difference, instead of sin you have tan. Third difference, it was for refraction, this is for reflection. This is for reflection. Fourth difference, that was for light, this is for actual mass colliding with something. Is that clear, everyone? With me? I can show you a beautiful example which was based on this question. There was a question like this, where they told that, listen, there is an inclined plane and the angle of inclination is basically 30 degree, and what happens is there is a ball which is dropped, but after the collision the motion at that instant is horizontal. Horizontally it rebounds. The question was, can you find the coefficient of restitution when this ball is particularly dropped from here? The ball is particularly dropped, it hits and rebounds horizontally on this inclined plane. Find the coefficient of restitution. Now initially the problem looks difficult, but with little bit of analysis, you realize it is not actually very difficult. See, this is the inclined plane. Okay. This is the direction along which the ball came in. After that, it rebounded like this. This is horizontal. Let me extend these lines. I think I'll be using division of 8 method. Let me extend these lines. Horizontal done, vertical done. Let's draw perpendicular to the inclined plane also. This is also done. Division by 8 method. Now my job becomes little easy. Observe. What am I trying to do? This is 30 degree, right? This was basically 30 degree. If that is 30, obviously this is also 30. Leave one side. This is also 30. This is also 30. Leave one. This is also 30. Every alternate one is 30, 30, 30 degrees. Okay. That is also clear. Next stuff. See guys, when it hits, okay, observe carefully. This dotted line is actually becoming the normal to the plane. This is normal to the inclined plane. So definitely this angle would be the angle of incidence. With the normal, it is reflecting here. This angle will be the angle of reflection. Is that absolutely clear? What is I and R? But I will be this angle, which is 30. So I will be 100% 30 degrees. Angle of reflection will be the complementary of that. So it will be 90 minus 30 degrees. So it will be 60 degrees. Perfect. My job is done. I had to find E, right? Which is tan of I by tan of R. So tan of 30 by tan of 60. Tan 30, 1 by root 3. Tan 60, root 3. So it will be just 1 by 3. So the answer is 1 by 3. Pure geometry question and just usage of this formula which I just learnt over here. That's why I said this is very important. Is it okay, my dear students? Understood how to solve these questions? These questions can come in your NEET examination. Okay, so we have done these kind of questions in 2 dimension as well as 1 dimensional question. Now usually there are names given in the textbook called as head-on versus oblique. What's the difference? See, if it so happens that the velocities are like this, this is called as head-on collision. This is called as head-on collision. It was highly inelastic in nature. Head-on collision means the velocities are in the same line and after the collision also they go along the same line only. But oblique collision is when one of them is at an angle. Any one of them or 2 of them are maybe at an angle. So that is oblique collision. That's it. It goes in some weird direction. You can see that. It goes in some weird direction. Even if one is straight, it's okay. You will see after the collision, that's it. They will go in 2 dimensions. This is oblique. Okay, the previous one was head-on collision. So this is all oblique collisions if you notice, because after hitting the surface, it is going in some different direction. So all these are examples of oblique collisions. Now there are some special cases which you should know because there can be some questions on that also. So first important rule which you should know, for elastic collision between same mass or same masses, the velocity gets exchanged. The velocity is exchanged. This is one of the first important thing which you should know. I'll give an example. Imagine there is one mass over here moving with some velocity, let's say u, and then there is another mass over here, identical, same mass. It is moving with some speed of v. This is before. After the collision, this is before. After the collision, what you will see is this particular mass and this particular mass, their velocities will be exchanged. That means this velocity will go to this guy and this guy's velocity will go to this guy. That's exactly what happens. The velocities get exchanged. This happens only for elastic collisions, that too for same masses. We can definitely see this in action over here. See, I have taken the mass of the red box as well as the blue box as 5 kg and 5 kg. Let me give this guy 10 meters per second, this is 0, and keep the elasticity as 1. That means perfectly elastic. This guy has some speed, this guy has 0 speed. After the collision, this will get that speed and this will get 0 speed. Observe this. Perfect. This stopped, that moved. Let's do it with some other speed also, it will still work. Let it be moving at some normal speed, 1.5, and let's see what happens. There you go. This got that speed and this moved with that speed. Let's take opposite directions and still let's see whether it happens or not. This is -5, this is 10. Perfect. That went faster, this became slower. Earlier, this was fast, that was slow. Now that became fast, this became slow. Perfect. This happens only when E is 1. If you don't take E is equal to 1, then it does not really happen. Be careful. So it is only true when E is equal to 1. Is that clear? So this is the first important property which you should definitely know. Yes, it is also called as soul exchange property or Atma exchange property. It's like these are two bodies and these were the souls. The soul of this went into this, the soul of that went into this. So it's exchanging their souls. Perfect. Yes, Krishna. You remember that example. Moving on to the next property. A large or basically a tiny mass colliding with a very large mass at rest. This is a very teeny weeny mass. It's going with some speed. There is a very large mass, much larger than small m. It is at rest. After the collision, what will happen? This mass will just return the way it came, and this mass will still stay intact. It's like asking, sir, if I throw a ball towards the earth, this is a ball towards the earth, what will the earth do? Do you think the earth will start moving? No, it will hardly matter, it will hardly care. Instead, the ball will go as it is. Approach speed will be the separation speed. We can see this in action also. Maybe we reduce the mass of the or the red box over here to very small value. Actually, I can't go less than 1. This is not going to give me correct answer. Let me go over here. Okay, mass of the blue guy 0.1. Not so much, but okay. This is 0 speed. This is coming with some speed over here. Let's see what exactly happens. See this? Tuck. Almost went back. There was some abnormality because it's not exactly horizontal. That's the problem. Otherwise, if it was exactly horizontal, then it will go with the same speed back. Are you able to see that? This happens when it is purely elastic. One mass is very huge, one mass is very small. So this is the second important rule while solving problems. The third rule, guys, the third rule which you should know is when a large moving mass, did I mention elastic at rest? Elastically, that was important. A large moving mass collides elastically with a small mass at rest, with a very small mass at rest. Let's take this. This mass is very huge, it's moving with some speed. After that collision, what will happen, we'll see. There is a very chintu mintu mass, much smaller than capital M. It is at rest. You will see after the collision, this mass will still continue moving with that same speed. Nothing will happen to it, but rather that chintu mintu mass will move with double the speed. This is very important. Double the speed. Yes. Yep. Double the speed. So let me show this to you via again that simulation. Maybe we can just keep it over here. Okay. And oh, I have to do it reverse. My bad. Okay. This is coming with some speed. And here is that chintu mintu mass, negligible speed. So let's see what happens after the collision. See this. Almost moving with double the speed. Wow, and there it got trapped. Okay, anyways, you can see this mass remains unaffected. This goes with double the speed. This is exactly what this is saying. So when a heavy mass collides elastically with a chintu mintu mass, the chintu mintu mass will move with double the speed. Yeah, very important rule again. Okay, very good. Last rule which you should know. For an oblique elastic collision between identical masses, one of them at rest, where one of them is at rest, then after the collision, they move perpendicular to each other. They move perpendicular to each other. What do I mean by this? Observe now. This guy is at rest, this guy comes and hits it. After the collision, they go perpendicular to each other. That means this V2 is basically perpendicular to V1. If one of them is at rest and the collision is elastic. Let's have a look at it. We need same masses, so let's keep the masses same. Oops. Okay, 0.99. It is 0.99. Oops. And hit same masses, guys. Little difficult to get it. I will try my best. My goodness. I do this, that doesn't come. Okay, almost close to each other. Okay, almost same masses. Okay, one of them should be at rest. One of them should be at rest. Just observe their motion after the collision. Just observe their motion after the collision. Okay, let's simulate this. See, they are moving perpendicular to each other. Again, observe this. I will throw it at a different angle. Still, their velocities are perpendicular. I will make it go like this maybe. See this? Perpendicular motion. Do you see that? If I make it go like this also, still perpendicular motion. Let me make it go little slow so that you can see it very easily. Maybe I go like this. Now also you can see perpendicular motion. So this is exactly what happens when the collision is elastic. one of them is at rest. So then you will see they both move perpendicular to each other. Is that very, very clear, everyone? Awesome. So these are the most important properties which you should know in collisions and momentum. Yep. So, I think by now you have visualized this entire particular chapter of momentum and collisions, and you have got a fair idea of how the questions work. And, I think after this, you would have realized that at the end of the day, it is just conserving momentum and using coefficient of restitution in all the particular problems. So guys, this chapter is done. Now I want everybody to comment day 1 done below, and everybody should start solving as many questions as possible. I have done all the standard model of questions over here. After this, I'm pretty sure you will see every previous year question or any question that you pick from any book for NEET, don't say JEE, for NEET, you will be able to solve those questions. It's some way or the other, somehow or the other related to any question that we have solved today. So just put in your effort, 100% you will be able to get it. And don't worry, there will be more problem solving classes in the days to come. Okay, God bless you all. Take care. Hasta la vista. Captain Shreyas signing off.